We
can suppress generation of excess pore water pressures, and as well with a small drop in saturation, can increase the cyclic resistance ratio of these soils based on lab studies. And also, as presented by Ed, we see that there's an economic advantage as well to MID compared to other treatment methods. Well, John didn't make the previous presentation, so this is all for his sake. But we see that economic advantage of using MID versus other ground improvement methods. So this is the site that we're going to tomorrow, and this is what the test setup looked like for us in 2019. We had our central injection well, and then 4 extraction wells that were spaced 3.5 meters from that central injection well. We had there's wires here that are connected to the control systems and the power systems for the submersible pumps. That are then extracting water to an extraction tank. Out of the picture, there's a tank where we mix the nutrients and then inject it through here, in this case with an inline pump into the injection well. There's also the monitoring systems we have set up at the site. This is an in situ array of moisture electric conductivity sensors that are installed at various depths in an auger hole. And then a seismic cross-hole array installed by the University of Texas folks back in 2019 to measure pressure wave velocities at various depths. And so with these data from 2019, we saw with the moisture electric conductivity sensors, the TERO sensors, there's a picture of them here, 3 prongs that get inserted into the side of the borehole. We could approximate the changes in saturation that took place at various depths. And at both sites, the Sunderland and Harborton site, we saw a reduction in saturation as read out by these sensors, and then also confirmed with, another source of evidence with the measured saturation from intact Shelby tube samples, and then measuring the saturation from those. So what we say, based on the samples and the moisture sensors, is that we reduce saturation to about at least 97% at these 2 sites. We also looked at pressure wave velocity measurements, and where we see a drop off from about 1,500 meters per second for fully saturated soils to less than 600 meters per second for soils with a saturation below 98.5%. And ongoing monitoring at the Sunderland site, we can start from way back here. Before treatment started in 2019, we see high pressure wave velocity measurements or values at all 4 depths in the cross-hole array. We see a drop during treatment that we can relate to the treatment. And then that drop in pressure wave velocity sustained at the site for about 4.5 years until about last September. Or last year, yeah. So last July when I got a call from Sung Moon saying the soil's saturated. I didn't expect it to be saturated. And Kayla, who took these measurements, says, oh yeah, the cross-hole data are also showing that we have resaturation as well at the deepest cross-hole sensor too. So maybe that saturation front is coming from below as the gas, the desaturated zone kind of weathers away. Then we see a bit of a response at some other sensors. Not really sure what to make of like these off measurements, but maybe it's kind of gas moving and shifting around in the system. I'm speculating. But what we know is that we did start to see resaturation at the site after about 5 years. These are the cross-hole measurements that Sung Moon and his team took last summer as well, at a different profile within the treatment zone. So our injection well, I think is right about there. No, I'm probably wrong about that. I think our injection well is here. So they're in the treatment zone, they're doing measurements. And as well, we see that these are the measurements in the untreated area, which we'd expect to be fully saturated below about 2.5 meters. And then these are the measurements in our treated area where we do see that there's maybe some gas still present throughout in the profile. But particularly here, we see an area of resaturation at about 4 meters depth. And I don't have them included here, but we do see there's profiles from 2019 that show profiles of like dropped in VP pressure wave velocity measurement through the whole profile. So So what we came to this summer is, can we successfully retreat the site? Can we perform MID treatment again and maintain saturation reductions or reintroduce gas to re-desaturate the site or re-reduce saturation ratios? We followed a very similar approach to what we did in 2019. Similar concentrations of the treatment solution, 0.12 moles per liter of calcium nitrate and calcium acetate, which we mixed in these totes here with a trash pump to circulate large volumes of the water. So we mix them, we transfer them into the injection tank, and then through a sump pump that's plumbed up here, we can then inject them into the existing injection well, and then also extract water from the existing extraction well. So less mobilization this year, more just coming out to the site with and getting a bit of equipment ready, and moving forward with the injection and extraction. These are our students, Fadza and Aman, who are out there all summer as they're doing pressure wave velocity measurements at the crosshole array. So with this treatment this summer, we did continual crosshole VP monitoring, just like in 2019 and the time since. We also installed additional Teros arrays for those moisture sensors in the ground. This is the existing array from 2019, and then we installed 4 others, one in the treatment zone, one at the edge of the treatment zone, and then 2 that are outside but at different distances as well. And with this year as well, we were able to monitor the injection and extraction rates at each well instead of just all the extracted water from all the wells. And so we have a bit of enhanced monitoring at the site as well. And I'll show a little bit. We also use some geophysics throughout treatment to track where the treatment solution is going in the subsurface and production of gas as well. So through this treatment took place from about July 31st until September 5th-ish. I want to say, or was it last Friday? Was it just last Friday? Yeah, September 5th. Yeah. So in total, we injected 48 meters cubed of the treatment solution, which is 45% of the treatment zone pore volume. So we got about half of the pore volume of water introduced into the targeted treatment zone. This is very similar to what we did in 2019. In 2019, we did about 50%. We were able to track the extraction rates at all of the wells this time around, and it was interesting. The black is the injected volume. And the extraction wells, the cumulative extracted water was able to keep up quite well with what we injected into the ground until about partway 20 days into treatment, where we see it starting to deviate. And that's when we had to start supplementing with additional groundwater. Looking into why we started to see this move away from a closed system partway through treatment, but potentially that's a sign that the reaction is happening and that we're losing the hydraulic conductivity of the soil and the yielding of the soil we originally had. This is results from one of the Teros monitoring arrays, the new one that we installed in the treatment zone, plotting time date throughout the summer from the time of started treatment, volumetric water content that's interpreted from the sensors, and then also the electrical conductivity. And so we see that at a couple of the sensors, we see that arrival of the treatment solution a couple of days into treatment, and then also a decrease, well, with an increase in electrical conductivity followed by a decrease, and indications that gas is produced, reducing the volumetric water content of the soil as well, at least a couple of the sensors in the array. So indications that that treatment solution is making it through the treatment zone again and producing gas. And then the important part that we were happy to see is the pressure wave velocity, the crosshole, which stayed high up until the start of treatment, and through the start of treatment decreased midway through treatment, indicating that we did have gas produced again at that crosshole array. I think that there's about it measures the pressure wave velocity between the receivers is about a meter between them. So within that meter, we had introduced some level of gas from the MID treatment, and so far the pressure wave velocity has stayed low. And then the other thing, I think, oh no, I don't have, this is again just reporting from a phone call from Sung Moon that I think it was yesterday. You're desaturated at the point where we had measured saturation previously. So Yeah, at the helical pile, we also show a saturation less than 98.5%. And then this is the geophysics that we implemented for the treatment this year. We did some testing with it last summer to see if we could see areas in which there was potentially gas in the ground. The idea that these electrical resistivity tomography surveys, they're measuring the electrical resistance of the ground. As we introduce the treatment solution and the solutes from the treatment solution, the resistivity goes up. No, wait, resistivity goes down. Its conductivity goes up. And then as gas is introduced, as gas is produced, those substrates are consumed. So electrical conductivity goes down, and then production of the gas also causes electrical conductivity to go down. So there's kind of competing signatures from MID treatment in the ERT, but it does give some indication where the treatment solution is going, and combined with some other data, we can also potentially see some signature of gas produced in the subsurface. And what we're seeing for this, or why we want to introduce ERT into our field treatment, is thinking about the way that this gets implemented in practice. As you're injecting the treatment solution into the ground, you want some kind of monitoring to see that the treatment solution is spreading throughout the targeted treatment zone. That's not just channeling through one area, maybe one fracture or one high conductivity layer. And so the ERT and being able to look at different slices of electrical conductivity in the ground and at various depths can give you some kind of assurance that the treatment solution is spreading throughout the targeted soils and at various depths as well, or that it's not, and that something needs to change for the treatment approach. So this is one of our implementations this summer, and this monitoring is ongoing, and also the analysis of the data and the surveys is also ongoing. So looking ahead, what we are planning to do at the site, now that we've seen that we're able to successfully retreat it and reduce saturation again, we're using the T-Rex to test with the enhanced shake testing. There is differences in pore water pressure build up between the treated and untreated soils. Continual analysis of the electrical resistivity tomography surveys, ongoing pressure wave velocity and TEROS monitoring as well. And then also next summer, or potentially, next summer, we're planning to do, part of the reason why we want to do retreatment is to do a pumping test at the site to induce fresh groundwater through the treated area, to then also monitor, kind of speed up time, so to speak, to monitor how saturation changes with that sped up time. So our conclusions from this work, we know MID is economical and non-invasive potential ground improvement approach for liquefiable fine-grained soils beneath existing structures. In 2019, we showed that it could be effectively applied to fine-grained soils, and that those reductions in saturation sustained for about 4.5 years. And then we saw that our retreatment this summer successfully restored saturation below 98.5% at the points that we were monitoring. And then finally, the work, this field work, both 2019 from then until now, there's a lot of folks contributing to it. So I just want to highlight the contributors, as well as like the industry partners that we have that have worked towards this and provided funding and in-kind support. And then also Portland Bureau of Transportation, their logo's not up here, but they have given us access to the site and ongoing access, which has been very valuable. Yeah, and so questions.
Can you go back to the ERT survey? So the red spot, is that an injection well, or
that's surrounding the injection well? That's that is the treatment zone primarily.
And when
this was last
survey taken compared to when the treatment?
So this survey, this was last summer. So this is like a baseline survey. Yeah, and this was interesting. So there was a red area right around the treatment zone. So there were some substrates remaining in the ground from MID treatment 5 years ago. And then combined with other electrical conductivity measurements, the electrical conductivity of the pore fluid itself was, I think, even higher than these surveys indicated, likely due to the presence of gas that's then reducing it in terms of this bulk. as essentially, yeah. But so, and yeah, what we're thinking is that as the emergence from this summer come through, we might see,
Growing.
yeah,
Because you use the same injection well.
yeah. Elena.
So a couple of questions. The first one is, how often were you testing compression pipe velocity over that 5-year period? Were you only getting yearly tests every summer, or were you getting them in the winter as well?
It was about every month. Let me see, about every month, but there were times when the array was submerged and you couldn't get out to it. So
What is your hypothesis on, especially during the dry season, on why that's when it went back to?
oh, like how it started to come up in about the summer and
Yeah,
then
instead of in the wet season.
Yeah.
What's your thought process behind that?
So I think that as far as like water table fluctuations, we've kind of looked at that and like because the water table at the site, it floods in the winter and it goes down to about 1.8 meters below the ground surface in the summer. So there's kind of this fluctuation happening. We don't see much in most of the sensors, we don't see a signal from that up and down in terms of volumetric water content. Most of them are just kind of steady and reduced. And so like Ed has pointed out, that water table is really, in this case, affecting total stress, effective stress. And so why this happened to go up in the I don't think it's in the summer versus the winter when it's flooding. I think it's mostly about what's happening in the subsurface for the gradients of the fresh water that's moving through. And maybe it happened in the summer because the gradients are higher, putting more water through in the summer. Maybe it's just the time that it happened.
Okay.
Or like there's also Aaron's model. Yeah, he looks at gradients of water and water flushing through, but there's also just like a dissolution and concentration gradients that are causing the gas to move out of like the gassy area.
Just another question, what PI were you? So,
Oh, PI is about 14.
okay, so.
Yeah, it's high. Yeah. Right.
I'm curious, does the vegetation have any impact on this different saturation? You know, it just looks like grass, but
Yeah, we don't really see. Let me look at a picture. So it was interesting. I don't think that the vegetation has any like what we're seeing 2 to 6 meters below the ground surface where we're treating. But there is going out there with geologists, they notice the vegetation. They notice not only like the area, like the ring that it floods, but also like they notice the change in grasses. Like there's sedges in some areas and reeds in another. And anyways, I'm not sure. That's yeah. So it's interesting to learn and repeat back, but I don't learn enough to repeat it back to you fully. So.
thank you.
Regarding the cost analysis with geographic, how long would it take for both of them starting at the same time? Start usually when the ground improved and ready to be delivered for them.
So the question is for the cost analysis. Oh,
Oh, it's not jet graph, penetration graph.
so yeah,
I'd have to go back and look.
yeah,
We-
but it's probably factored into this equipment and labor
Yes.
per hour. So
I remember from the carpenter that MIDP takes longer,
No, less,
shorter.
shorter. Because you only need 1 pore volume with your maybe.
Have you considered like durability of those tests? Like this is just MID is for 4.5 years. What about this permission? Like how long?
oh, that's forever. Well, forever. Yeah, that would have to be factored into this. So I probably didn't underscore this enough. The MID in this case was 4.5 years. And that we need to look further into just why it was 4.5 years. This is our first injection. And so when we did the first injection in 2019, it's quite possible we opened up some space in the ground. And like that's maybe why we were able to get those nutrients there. But is that providing a path for fresh water to come in and desaturate or resaturate the ground? So MID in this case at this site with this treatment was 4.5 years at that depth. It's a specific case study case.
And it is a little curious, because I would have thought, once we desaturated a fine grained soil like this, it would persist for a long time due to surface tension and holding the bubbles in the pores, that it should persist longer than sand, but this suggests that it's faster than some of the cases we looked at for sand, so.
Yeah.
It's curious. That's why it's research.
Fun.
On that note, you mentioned your geologist, but does the area have like a regional groundwater grading? Is the groundwater shifting out towards one direction or another?
So that is a very good question. At the site, that's not a good picture of it, but you can see how close we are to the Columbia River. And it's kind of, it is a floodplain down to the Columbia River. We're about 500 meters from it. So I had thought that there would be a gradient towards the Columbia River. If there is, it's pretty minor. Then again, we only have wells spaced 7 meters apart to look at that gradient. But what there is at the site is just to the west of it. Right here, there is a levee and like a drainage canal as well. So that could also be influencing and maybe pushing. And that actually is something that we've discussed. When you look at these ERT surveys, so the drainage canal is here, and we do see that the treatment solution, like the substrates, are kind of being pushed out to the east, perpendicular to that drainage canal. So that's possibly where the prevailing gradient is. Yeah.
Yeah. So like you said, like this MIT is for existing structures. So did you consider the overburden pressure when you're doing the treatment?
Okay. So it's it's economic for existing structures. That's where you see the economics come through. Do we consider the overburden pressure when doing the treatment? It was factored into the injection pressures so that we weren't fracturing the soil, like, yeah, so those can provide some confinement. We weren't overcoming those to fracture the soil. But that is an area where like we'd want to be looking more at the control of the injection system.
There is another issue in terms of amount of gas you need to desaturate the soil as it gets deeper, because the steady state pore pressure is higher. It'll absorb more, well, it'll compress the bubbles in the nitrogen, because that's the best way to say it. So
Yeah.
you need to generate more nitrogen to get the same level of desaturation, because you have a higher pressure.
And I'll say that FADSA is looking at this with seepage tank experiments in the lab that we borrowed from Arizona State, right? To look at those seepage tank experiments, instead of 1 foot of overburden pressure, adding overburden pressure to see how gas production venting changes. All right. Okay. Thanks, everyone. So up next. Oh, wait, we had questions.
Oh, this okay.
Oh,
Oh, no,
the
those are
timber piles.
yeah, that we have vision.
Yeah, we're gonna call this one for head. Okay. Do you want me to pull up Arash's?
Oh, it's mine.
Oh, it's yours.
Yes.
Let's do it.
What's this? Yes. So it's me again. We'll talk about field nonlinear cyclic measurement is. So the nonlinear measurement is important because to understand the soil response during the earthquake, and the motivation of our research was Like during the earthquake, the soil will respond as they do in the laboratory. So does any like natural environment reveal something different? So that was the motivations, and we are trying to address this by using our new testing method. So here's our outline. I will talk about the importance of the nonlinear soil characterizations and why important, and compare the lab and field testing. So make it how to measure the nonlinearities. And I will talk about the field testing that we done in New Zealand. The purpose of the project was the shallow ground improvement evaluation project in New Zealand. That's the biggest project we involved to do a nonlinear field testing. And we will give the reason, like Sunderland site, a result to show how much we have improved our testing method, and I'll make some conclusions. So why nonlinear soil property measurement is important? So everybody knows. So soil exhibits strain-dependent behavior. So we have larger displacement, larger strain that gives the stiffness decrease and then damping increase with shearing strain. So accurate geometry max will come from essentials. If you fail, then that will result into the inaccurate ground motion predictions, and also for the liquefaction assessment. Typically, we measure the nonlinear behaviors of the soil using the laboratory testing. The majority are for the NQA1 level project for the nuclear power plants. They have to do like a nonlinear testing. I'm from UT and learn from Dr. Suki. I will give you the example of RCS testing and the testing results done from the RCS testing. It will provide controlled and high precision measurements and can reach to moderate to larger strains up to 0.1%, depends on the soil type, can go up to 0.2%. And however, it's limited by the ideal sample. So there's a possibility of disturbance. Once you sample, you have a possibility of disturbance. When you extrude the sample, you have a possibility of disturbance. And once you try to carve and try to trim it to fit your apparatus, there's another possibility of disturbance. And once you see the data and something seems not right in what we were going to say, okay, the sample is disturbed. So laboratory tests often cannot fully replicate the field condition. On the right side, the field testing, well, I think the UT was one of the facilities trying to do the nonlinear measurement in the field. And so we were testing the field to capture the realistic field conditions, cannot combine pressure saturation and natural layerings, but we cannot get larger strains. To the right side, this is showing our testing scheme. So we have the embedded sensor in the ground, which generate the wave on the surface. And that doesn't really give a larger strains and reliable measurements. So I will show you by the example of the biggest project we have involved. So this is really a famous picture. So once you Google a liquefaction in car, and this picture shown. So this has really happened during the Christchurch earthquake in 2011. 6.2 magnitude earthquake hit, and the major damage was from the liquefaction spreading. 25% of the New Zealand GDP was lost during the liquefaction. And it was not just, there's a lot of call like this, and this is another picture. There's the sand ejecta from all over the place. The problem is, though, people still have to live there. Government cannot ask, okay, you just live the other place. So they have to rebuild in a land the possibility of the liquefaction in the future earthquake. Therefore, New Zealand, the government, have to find both cost-effective and simple approach to increase the resilience of the buildings. There's 4 or 5 examples actually. There's rapid impact compaction, so they compact the soil. Ram aggregate pier, so stone column. Low mobility grouting, and they have a single row beams. And they create one column row of beams in between the liquefiable soils and the non-liquefiable crust, and put the dome row beams. They have this 5 ground improvement method was prepared, and the UT was selected for the test evaluation their ground improvement method. Here's the schematic. Well, there's like a plan view, the cross-section view and plan views. Before we start with the liquefaction, our conventional liquefaction testing, we always have to do a cross-hole testing. The cross-hole testing is so it's a conventional cross-hole testing. You need a borehole, and that borehole costs quite because we have to have 3 boreholes that cost a lot of money. So we developed the method called direct push cross-hole. We use the CPT mechanism, push out a rod. With the end of the rod, we have a sensor, and we push the sensor to the depth of interest, and we tap the either end. The wave propagate through the single layer at the same confined pressure. And this is the most, I think, highest resolution profile you'll get in terms of VP and VS. I will talk more detail later. So the cross-hole result, the shear velocity, give you this small strain measurement, and that will give you the correct Gmax. Measuring the Gmax is important because for the nonlinear property, so you end up with getting like G over Gmax versus strain like plot. And the Gmax is wrong, then you will divide every G by the Gmax, so that that curve will be misleading. So the cross-hole have to be performed before do any kind of nonlinear testing. Try to prove how effective their shallow ground improvement was. We have zone A and zone B. So zone B is where this is the example of route. So they put the stone column. It has to have a higher shear velocity. They put the stone column on it. We don't care. We really care what's this zone A. So between the improvement, how they effectively like increase the stiffness in situ, those are the first thing. And then we run our conventional liquefaction testing. We have the pore pressure at different depth. We have the geoflow to measure strain, and the vibration is happen on the ground surface. And this is the cross section is showing like how we are positioned between the wrap. And I was simply just talking about the result. So PA velocity, as Dr. Kavzan mentioned during his presentation, the 0.6 meter was their water table. It wasn't saturated. It saturated started at 1.5 meter. So Dr. Kavzan was correct. And one thing noticeable is here, LMG. So I think Diane had to talk to them. They desaturate the soil. And I think those are good for liquefaction, right? Desaturate soil. Why that happen? I will talk into later. And this is the shear velocity we measure in the natural ground. So we have to measure the natural ground because there's going to be the baseline, try to compare how the ground improvement really like increase the stiffness. So there's a comparison. Left side is between the improvements, so how they like increase the shear wave velocities at like the improvement zone. Wrap and rig like increase the shear velocity like 10 to like 15%. LMG decreased to like 20 to 30%. So when they injected the LMG, they actually heat the soil up. So that create the desaturations and lower the shear velocity. So what I know is the LMG was never like implemented to New Zealand for the ground improvement method. Well, I'm not talking about energy is bad, but this is just for this case, I will say. I present this result in the routing conference, and there was a lot of arguments. And they said, okay, those are just like certain like practitioner can do it. And that was true. So LMG has to have a column, but there wasn't in the location they're supposed to be. They have like one bulb here, other bulb here. So even if we cannot finish our testing, because when you proceeding the rod, we hit the LMG, it's supposed to not. So there's some argument, and Krasuki show up and he said, okay, so anybody want to test their LMG, we can do it. Raise your hand. Nobody. So that was it. Oh wait, Dr. Suki back me out. So these are the nonlinear measurement we have measured. This nonlinear G over Gmax curve we measure from the lab. I will show you why. And this curve is from the reconstituted sample. Why? It's hard to sample the sandy soil, liquefiable soils below the water table. You cannot. Well, it will be hard. Somebody can do it, but I didn't get it. So we did the RCS testing to measure the nonlinearity. This is the nonlinear measurement in the field. We have the strain versus the pore pressure. So what we say, okay, we have the geometry max, the pore pressure will be built up around 0.02%. So this like reduction will be larger. That was what we measured before. And now what we are trying to do, we are trying to measure those geometry max in the field. So these are the limitation of the conventional method. So Shear can apply at the surface, and that should already propagate through like during like the varying stress across the layers, and there have a rapid attenuation of the cyclic strain with depth. The 0.03% the shear strain we measure from the 0.6 meter geophone. So the effective testing zone is restricted to like 2 meters. So we need like somehow propagate our vibration to the depth of interest. And I think I showed you some of the pictures in the first presentation. So we have the helical pile. We install the pile to the depth of interest. So this is the case of the Sunderland side. We installed at 2.9 meter. We put the thumper on the top of it. And then we install the geophone and the pore pressure at the same depth of interest. So the wave propagate horizontally, like crossflow testing. And we put the thumper on the top, we shake, the vibration transmit to the depth of interest, and then we got the wave, and we can calculate the velocity, shear and strain, like pore pressure buildup. And why use the helical pile? So helical pile consists of like central steel shaft with one or more helicals, and is supposed to siphon the soil, not displacing or hammering. So it preserves the surrounding soil fabrics and stress conditions. And importantly, the disturbance is localized to the narrow path of the helical plane. We got luckily that there's a professional like helical pile company near Austin, like 2 hour drive. So this helical pile was like custom made with the discussion with the professionals. Here's the examples of helical pile installation. So these are the Sunderland side installation. We done it last week. So when you see this video, there's no like soil like shoving out from the ground. So that means like, yeah, it's like a screw. Like we're just placing a slicing, not disturbing the soil. We need it because like our sensor had to be closer to the vibration to the helical piles. Once we installed helical pile, so we installed our 3D geophones and the water pressure transducer at the same depth. So it's custom built, it's a polycarbonate casing. So to try to get the similar unit weight with the existing soil is 100 PCF. So we have 3 orthogonal 28 Hz geophone to measure the particle velocity. And here's the pore pressure. We can measure the static and dynamic pressure of the water. And we put the thumper on the top, and thumper is good for this testing because we can generate like high frequency result that we can have the Gmax, and then we can like proceeding with the low frequency with the larger displacement. So this is how we looked once we finished all the installation. We have 3 3D motion sensors, and we have the PPT at the same depth at 2.9 meter, and then we have a pile. So we think in a way it is good testing method. But once at the time we have all the instrumentation for the liquefaction testing, the problem was we don't have a site to verify because we cannot do it in Texas. Texas, the water table is deeper. And like the stiffness of the subsurface soil stiffness is 3 times compared to the Sunderland site. That's the modulus is 9 times. So Texas has a 9 times stiffer surface compared to Sunderland site. And at the same time, we got a phone conversation with Dr. Cavendian, and he was trying to looking for some of the testing methods they can like evaluate the effectiveness of the MID treating pad. So this project was kind of initiated the mutual interest. But Dr. Cavendish wasn't like easy, right? So he said, you have to test it at the natural location, right? First, and you prove it is working. And then you can come to my MID pad. If not, you are not going to go get close to our MID pad. That's it. So We will, yeah, so we are trying to measure the nonlinear behavior at two pads. So here's the untreated pad and the treated pad. It is also shown in Diane's presentation. So this is the MID treated 2019, and also we do the protocol testing and CPT testing in 2019. Yeah, so they have a lot of like testing technique that done in the area, but it wasn't happening before. The first thing what we done is we went there and we will run the CPT. Try to run the CPT, try to find the closest, like similar to the MID treated pad, the soil type. So this is Mogaro. It's also the CPT run in 2019. This is the black line. We run CPT 1, 2, 3, 4 locations. And I think it was most, the board, all of them are similar. And to the I sub C is 2.6 to 2.95, related still to the silted clay. And the CPT one is most similar, but it's most close to the Mogaro's published the data. So we select CPT1 location at a natural pad, and another reason is it's far from the MID treated location, so they're going to be less influenced by the MID treatment. So we found some error dislocation while we're doing our helical ball testing, and then what we have to do, run the crossflow testing. So this is the schematic of generalized arrangement for the direct push crossflow. We have a pushing mechanism on our back of a T-Rex with push the three rod at the end of the rod. So there's going to be joke from here and here and there. We hit it, the wave propagate through the rod, and once you touch the end, the wave propagate to the SV wave, the horizontally propagated in the vertical particle motions. So we can measure the P wave, S wave, and we have like 3 direction of the sensor, so we can also measure the P wave. This is the pictures we take in the labs here. So we did the crossflow testing. Here's the CPT mechanism back in the T-Rex. We push the rod, push the rod, we get the wave propagated. And at the end of each step, and then we keep proceeding and deeper, and we got the profile. And then I think it also presented in Diane's presentation. This is a P wave. This is 2022 compared. And here's a shear rate. It is similar. It's really similar to the MID treated pad, but between 3.5 to 4 meters is little like low. So we were trying to have the closest possible, the shear rate stiffness and the material type to the MID treated pad. So we selected 2.9 meter. So it's like water saturated, and the shear velocity is similar. So we picked the location, and we installed the sensors, and after that we put our thumper on the top of it. So this is the whole force is like the minimum. We are trying not to push the helical pod to try to have the pressure pressure influence. So generally, we put it on the top of it, and we shake. Here's the result. So this is between the 1G and 2G closest sensor and the second closest sensor, as an example. So so it is 200 hertz, sorry, it's not 100. So we shake it at 200 hertz with 30 cycles, 24 full cycles with 3 taper signals. And what we can do with this measurement, we can calculate velocity from, I chopped all the signals by one cycle. So I calculate the phase difference, calculate the velocity. You can do like cross correlations, or you can just pick each peaks and calculate the velocity, because you know the time difference and you know the distance between the sensors. The velocity you'll get is 125 meters per second. It is exactly the same with the crossflow result. So there's no disturbance during the helical pulse, and we are satisfied that we can get the G math matchings with helical pulse testing and the crossflow testing. You have the shear velocity, you have the unit weight, the unit weight multiplied by the square of the shear velocity, you will get the G. So G was like 13.5 megapascal. Another thing you can measure is this is the voltage level from the geophone. So those are measuring the velocity. We calibrate all our sensors, so we know the calibration factor. velocity and change it to the velocity. And we use the trapezoidal like integration to calculate displacement. So you know the displacement between 1G and 2G, and you know the distance, so you can calculate the shear strain. So the shear strain was 0.00137. This is our test result. We already run it last year, and this is our field testing result, 30.5 megapascals. And the large test result showed 30 megapascals. So minimum surface, we have matched with field and lab. Great. Now we go down to the lower frequency to get a larger strain. Okay, so and the PPT reading was, well, it's just small shaking. It's like 1 centimeter or water fluctuating. We proceed with the different frequency, 150, 100, 80, 60. And this is a signal from the 50 cycles, 50 hertz. So this is the maximum shaking, 50 hertz wave for 44 full cycle, 3 tapering cycle, taper signals, and the largest voltage input. We calculate the same way, calculate the velocity of 50 meters per second, and that gives the G of 3.4 megapascals, and the strain was 0.3%. And this is the last point. The PPT readings. So we generate like the water fluctuating for like 24 centimeters at the natural pad, but we don't see any kind of the pore pressure buildup. So yeah, we think this site will have to have a larger strain to generate the pore pressure. And we fit the hyperbolic model. This is just using this equation, and those two like solid line and dashed line will be presented in the very last moment just to compare the difference between the MID and the natural soil pad. So this is, yeah, so and then we go to the treated pad. The first time we'll try not to do any cross hole at that MID pad because we're trying not to poke a lot of hole, try to mess up with their like bubbles. This is actually done it afterward. We've done the helical pod testing, and this is the time when I call Diane. So this is not really, so it's a partially saturated. So you see the 90%, 99%, the shear P wave is high. So our depth was 2.9 meter. We saw like partial like increase of the shear velocity. So I called Diane. So you have to come here. P wave velocity, sorry, P wave velocity. It's partially saturated. So you see, we run the crossroad testing, the 2019 and 2024 last year. So this is like why the crossroad is reliable. You exactly have the same stiffness profile. But the shear the P wave velocity was showing like partial saturation. So the P wave had to be like 500 meters per second once there's a MID trim effect. So we do the same thing. We do the lab and field, but actually this time we have some lower velocity in the field compared to the lab. And I think there have some small disturbance from the power insulation. But like, so the velocity itself didn't look like too different, but you have for the calculate the model, so you have to scale it. So that's the reason it seems like a lot of difference, but into the velocity, you'll say, okay, maybe some. The PPT readings for the MID pad, so they were a little less. So pore pressure, the maximum of the water, like for the dynamic signal was 20 centimeters as compared to 24 is less. And interesting, this is a negative pore pressure buildup. So actually the soil was dilated. It's like clay kind of soil behavior. That was really interesting, like that we found. And we also put the G over Gmax, like divide by the Gmax values and then do the modified hyperbolic models and compare the data. So all the solid line was the RCS testing, and the blue is the treated and the green is for the untreated. For the field testing is all the dashed line. Treated is the blue and the field is untreated. For the field is also dashed with the greens. So below 0.001% strain, where it start kind of like kind of linear range, you just match like together. Those are exactly the same thing. But like after 0.01% strain, the field test is big for the nonlinear than the laboratories, right? It's a little more larger, like lower. And I think we run another testing last week and I tried to find out why, and it might be because of the pore pressure buildup, but our pore pressure is not reading correctly. But I think what we have found is like maybe when we have a larger strain with a different frequency, our Gmax might be a little different. So we have some additional test data set last week. So once we correct it, I think it's going to be more close to our test result and there's no pore pressure buildup. It has to be. So treated pad demonstrates a slightly higher stiffness, both for the RCTS and the shaking testing in the field. So the both test methods show the consistent trend, so we are really satisfied with that result. Then here's the summary and the conclusion. So field cyclic testing were conducted at the Sunderland site to evaluate the effectiveness of the MID, the method that applied in 2019. So we have measured the nonlinear behavior like successfully for the both pad, and in which the data is comparable to the RCTS result. The pore pressure, there's no like excessive pore pressure buildup for the dynamic pressure. We saw 20 centimeters to the 25 centimeter at both testing pad. We saw the treated pad exhibit slightly greater leak factor resistance after the strain exceeding about 0.1%. But however, there was a desaturation effect in the MID method, was not evident in the treated pad. So there's some limiting to the reliability of the result. So further study need to be pursued. But that's the reason Diane do a retreatment, and we tested. They should do some testing last week. So I hope that we can have more understanding on the soil non behavior in the future. And thank you for NSF to have financial support and develop operating the UTexas equipment. And also thank you for Dr. Gavin Benji and also Center for the Biomediated and Bioinspired Geotechnique. And special thanks to Dr. Gavin Benji and Dr. Arash and Diane for giving this wonderful opportunity for the collaborations. Yes. Thank you. Yes. Yes, any questions?
Is there any special reason for up to 4 to 5 meter? Is it because the effective design that's
Oh yeah, the crossover testing, or when we moved to 5 meter. We went to the 2.9 meter for the nonlinear testing.
But basically, it was for shallow depth.
Yes, so those are the effective zone of the MI treatment between 1 to 5 meter, right? 1 to 5 meter, MID. Yeah, so we choose the close to between the MID and the natural pad to pick the 2.9 meter measurement. Yes.
Simon, do you push your sensors in before the helical pile, or
No, we put the helical pile first and then push the sensors.
saying to reverse that order so you can see what pore pressures and strains are generating
During this? I think we also thought about it, but the possibility that so we install the sensors, put the pile, something happened, break the sensors, and then we have to do it again. So what we do is we push the helical pile first, and then we push the pilot rod at the depth where we expect to hit the helical. If we don't hit it, then we install the sensor. That's the safest way.
So
we do.
Follow-up question is, what's the vertical displacement from that you're producing?
So strain, so the strain rate is strain was to smallest 0.001%. I didn't have the number in my head.
Generating weight above and below whatever the helicopter, will that cause pore water pressure to move into the envelope?
Yes, there's some possibility, but we cannot really know. What we really need to know is they didn't generate pore pressure. So we run some try to build up the pore pressure. We shake using with 1,000 cycles. After that cycle, we saw the pore pressure build up, but not building up. So we have it give the negative pore pressure. It's expand. It's like a clay material, and then slightly increase and it dissipates fast.
Go stick a pore pressure transducer on your helical pile.
We will try to have one inside, but no, I think we cannot measure it. So yeah, we'll also have some crazy ideas, but it wasn't possible. Yes.
Could the lower stiffness of the lab samples be due to some disturbance due to the release in the gas pressure.
Oh, I think there's yes, still some of the possibilities. So we don't.
Can be corrected to the line of gas between in-situ pressures and atmospheric pressures.
Okay. Yep. I just showing the test results. Okay, so we like say okay, we said this is lower than the field. Yeah, something maybe disturbed. That's what I just like think, and then I didn't think more about what it happens. And any other questions? All right, thank you. So, Rush. Yeah, go ahead. I don't know where the presentation is. It's on celebration.
I think it's already open.
Yeah. Alright. And then I will like start sharing the. Yeah. Oh, I mean you can print it. Like. Your first. Or do this. Oh, like where? This. Let's go to.
So my presentation is is not related to MID. It's mainly related to comparing the cyclic shear tests that we did at PSU with the Shelby tubes that University of Texas took from the site last year, and comparing them against the field testing that Sungmoon just showed. Trying to see, are they comparable? Are there things that we can learn? So so as the practitioners, local practitioners in the room, we have a lot of low plasticity silts in our area, in Oregon, Washington. This is a map of a database that we've been working on that includes the cyclic tests that have been performed on real projects, mainly transportation projects, and have been donated by many of you practitioners in the room to most people refer to this as Steve Dickinson's database. So this is the same database that Dan and I worked with Steve to finally publish them. So the results were published in a 2022 report to ODOT. You can look at the data. There are data from Oregon, Washington, British Columbia, and Alaska on silt-rich soil. So non-plastic, low plastic, and plastic silts mainly. One of the things that we found looking at the data in this database, which a lot of people have witnessed before too, is the dependence of cyclic resistance to OCR or stress history. So here you see the cyclic resistance ratio on the vertical axis versus over consolidation ratio. And as a lot of people have reported, it increases with OCR. You see data here from Washington, Oregon, some data from Bootlegger Cove in Alaska, and also tidal silts in Alaska, and other studies too, from Vijay Karimi, British Columbia on Fraser River silt, Dahl et al., the UC Davis test. I made this figure before Armin's data was published, but I think the tests that Armin at OSU and his students they've done, they also show an increase or the effect of OCR on cyclic resistance. So, which is not really surprising. The OCR, it does affect cyclic resistance ratios. So the question is, how do we account for that when we do cyclic testing in the lab? Again, some of you may know, we do cyclic testing, CDSS testing for consultants in our lab. OSU does that too for projects, which if I give credit to our two universities, I think this has in the past few years, doing this, I believe has contributed to the profession. So now you don't have to drive the samples up to British Columbia. There is that capability here and at OSU. The testing parameters are usually decided by the geotechnical of engineers and or the engineer of record. And I know some of you have preferences on how you want to consolidate your soil, whether if you want to use recompression versus Chancep, what methods you use for evaluating OCR. But sometimes we get questioned that, what do you recommend? And our answer is usually we don't know. We know that it affects, and so some of the practical questions, how do we estimate OCR for these low plastic seals? We know that the consolidation curve is very curvy, so how do we estimate OCR? And then if once you've come up with that, how do you consolidate the soils in the cyclic shear device? Recompression versus Chancep type approaches, and they all affect the result. So this is result that we just recently published. This is Amir Baratini. Is Amir in the room here? Okay, so Amir, this is GeoCongress 2025. He's close to graduate, so if you have openings, we'll talk to him. So what you see here is the CRR for Chancep-based approaches versus CRR using recompression. And the ratio ranges somewhere between 1.2 to even up to 3.4-ish. There's a data, one of Armin's test data is there. This one, it's pretty unique case, OCR 11. So all the consolidation tests, and this is a local project, Beaverton. So these are Missoula flood deposits, shallow soils. Consolidation tests, CPT data, the consultant's knowledge from adjacent projects all indicated that OCR is high. So if you test them at that OCR and use Chancep approach, you get about 3.4 factor higher cyclic resistance than if you do recompression. So these data points, we oftentimes when we do the testing, we ask the consultants if we can take the leftover soil and do, if the tests were done with Chancep, we do that extra test with recompression. So all tests come from the same Shelby tube, same in situ stresses, but one done with Chancep, one with recompression. So we thought that with this project where University of Texas was able to do the field testing, we thought that maybe we can use that data to see can we inform these two questions about how to estimate OCR and also which method to use in our CDSS testing. So you've already seen a lot about our Sunderland site. It's located right to the west of the airport. I hope many of you can get to come to the site tomorrow and see the site in person. Here again, Sang-Moon just showed this map. This is where our MID treatment is. These Shelby tubes that, or the tests that I'm going to be talking about are from what we call the untreated path. So over here, where they did their nonlinear field shaking with thumper and the helical pile, and then they took a few Shelby tubes. They took some of them back to UT. They did RCTS testing on it, and we took some Shelby tubes to PSU, and we did CDSS testing. So a little bit about what type of soils we were talking about. So again, someone already mentioned that they installed the helical pile at 2.9 meters. So the field testing is representative of the soils at 2.9 meters, I'm sorry. So 9.5 feet approximately. So you can kind of see the CPT results, the soils pretty low, tip resistance, about 10 TSF or so. ISFC, as many of you might be familiar with the type of soils that are around the airport. ISFC range is about 2.9 to 3.1. And that's kind of what we have over there too. And right here, this dash one shows where that Shelby tube number 3 that our CDSS tests were done were from that Shelby tube. Shear velocity again, measured by the University of Texas, somewhere around 120 meter per second. And someone already explained the rationale for picking that depth, which was right below where VPs are high enough, indicating full saturation. So these are the soils that we're comparing. And again, we have the data from the helical pi test, and we have data from the test that we did on that shoulder tube that you see over there. Again, some index properties about the soils that I'm talking about is a low plasticity silt ML type soils, PI kind of ranging around on average 16, fines content, pretty high fines content, 90 to 95%, and the silt percentage is about 70% or higher. So Kayla did these tests, and many of you know Kayla. She's done a lot of the tests that we've done for consultants. So these are the tests that Kayla did, consolidation tests. Look at the console 3, that's the Shelby 2-3, so the blue lines. If you use Casa Grande method, our best estimate pre-consolidation stress comes out about 230 kPa. If we use, so 230 is 100, 230, right about there. If you use the strain energy method, it will be lower, somewhere around 75 kPa. Was there a question? Oh, sorry. So going back, 230 kPa using Casa Grande, that gives us OCR 7.5. Lower pre-consolidation stress results in about OCR of 2. Now, interestingly enough, these are the results from the RCTS test that Professor Sokin and his team at UT done. So these are, again, from resonant column torsional shear tests. You're looking at the shear velocity on the vertical axis and the isotropic confining stress on the horizontal axis, where this slope changes appears to be where you transition from NC to OC. And that is about, 45 kPa or something in that range. That's isotropic. If you assume some K naught and convert it to a vertical stress, you get something about 67 kPa. So that's just kind of another data point to see if you're looking at Casa Grande method versus the strain energy method. This matches more with the strain energy method. But we wanted to see how do we compare the pore pressures developed in the field versus what we get in the lab. So we did 8 intact samples, so 8 different strain controlled CDSS tests at 0.3% shear strain, which was, if you recall from Song Moon's test, that's 0.3% is the strain that they achieved in the field at 2.9 meters. So we tried to replicate that, but we also did at 0.6% to see how pore pressures develop with shear strain. We did our test with OCR 7.5 based on what we came up with the Casa Grande method. So we loaded to 255 kPa, unload to 34. But we also did at other OCRs, so OCR 1.5, OCR 1. We also, for fun, we did a recompression method. So basically just loading it to in situ vertical effective stress and then proceeding with cyclic tests. So here you see the vertical axis is the residual pore pressure after 50 cycles, which I think the field testing was, what's the equivalent number of cycles in the field testing? 40? Is it 50? Okay, so that's how we picked 50 to be kind of comparable to field testing. So OCR 7.5, you're pretty much in the dilated zone, or negative pore pressure. 1.5, you're over here, and as OCR decreases, this moves up. Recompression is significantly higher pore pressure compared to when you're using chance-dip approaches. So then we said, all right, well, this is expected. This is what you expect to see, but which one is correct? So we thought we would compare to that one data point that we have from field testing. And again, it's just one data point, but it's an important data point because it's the field testing, less disturbance compared to preparing intact samples. So we wanted to see how they compare. So these are again the results that Sung showed in his presentation. Shear strains in the 0.2948, so roughly 0.3%. And when you look at the pore pressure ratios, it ends up being almost zero at the end of 50 cycles. If you put that point over here, that square is the data point from field testing. And when you compare it against OCR, it's, it matches better with the OCR of 1.5 or 2 that we estimate using the strain energy method, and not necessarily the higher OCR. Again, just one data point, and you have to kind of treat it as is. It's just one data point. It's you can't really. I want to avoid extrapolating it and making a solid recommendation, but it's an important data point. So the CDSS specimens that you consolidate using the Shansep type approaches, where you can load to a certain stress and unload back, underestimate the pore pressure that we develop in the field. If you come up with your OCR using strain energy method, you're pretty close match. If you use recompression approach, higher are you. So that's kind of that, but we also wanted to see how can be projected the pore pressures to higher strains, and we use the Vucetich and Dobry's pore pressure model for sand to fit to our data points. We have a paper where we took the Vucetich and Dobry sand model, and we calibrated to the strain control test data that we had in our SILT database, and we came up with these constant parameters for silt soil. So it's Vucetich and Dobry sand model, but it's calibrated for silt soils. And if you're not familiar with the Vucetich and Dobry sand model, this is RU, and it's a function of number of cycles and your shear strain. All the other stuff in this equation are constant parameters that we came up with an equation for those based on the data in our database. One thing I want to mention, because this relates to the field test that they did in 2019. This parameter here, gamma TVP, that's the threshold shear strain for developing pore water pressure. It's a pretty important parameter. So Professor Vucetich and Mortazai in 2016, they updated their model for the threshold shear strain for pore pressure versus PI. They came up with these dash lines. Armin and his team, they had a point from the 2021 data that falls right here. We had 4 data points from the test that University of Texas did at our site in 2019. We looked at the data, we came up with the threshold shear strain for pore pressure, we put them on this plot. It pretty much is bounded with those dash lines that Vucetich and Mortazai came up with in 2016. So we felt like that's probably there. We don't need to really update that. That's a good this equation right here. That kind of approximates the middle range of the range that they provided. So then if you use that, this is kind of how we project it up. These are our 2 data points from our Cyclic DSS test. That's data point from the field testing last year. And then if you use Vucetich and Dobry model, it would project it up. So for this soil with that PI and that OCR, we would expect to get to something about 70% RU at shear strains exceeding like 2 or 3%. But again, that's just a projection. It's a predictive model. It's not lab tested. So again, conclusions, mechanical consolidation in the CDSS using the Shansep type approaches If you come up with your OCR using Casa Grande, may underestimate the RU that we measured in the lab. If you estimate OCR using the energy-based method, that closely matches the RU in the field. Recompression method overestimated RU from the field. And then potential future work. As some of you may know, the UT team took several Shelby tubes past couple days, and we're going to distribute that with some of the workshop participants that express interest in getting a Shelby tube. So some of the additional work that I think we can do, at least related to the cyclic behavior of soils. There are other things that can be done too, but for the sake of cyclic shear behavior, we can, I think it would be interesting to look at the dependence of or repeatability of data between different labs. Constant volume versus truly undrained. The test that we've been doing is constant volume. I always wonder if the pore pressures that we back calculate using constant volume, how accurate those are. So if any of the people that have expressed interest in getting a Shelby tube, if you have a truly undrained, I don't know how there are issues with using a truly undrained device for sill soils too, because the pore pressures it's going to take a while, takes time to equalize. But anyway, that might be one thing to look at in the future. Different consolidation approaches. You can come up with many different ways of doing recompression and also shan step. So there are other ways that you can look at it. The tests that we do, we have our consolidation device at PSU is the incremental load. We don't have a constant rate of strain, but that might be another potential thing to do is with these new Shelby tubes to look at the constant rate of strain and see what kind of OCRs and pre-consolidation stress you can come up with. Yeah, so thanks to NSF. I think that's been a common funding source for a lot of the presentations in today's workshop. Even though this particular testing was not part of any of the NSF work, but the PIs on this project have been funded through NSF during this work. And as well as the NHERI at UTexas that has been great to work with doing the tests, sharing their data with us, lab tests as well, not just the field tests. We really appreciate that. It's been great working with you. As well as I really want to mention the geotechnical engineers, our local geotech engineers, really the value of the data that you donated to the database that we've been developing and being willing to share that data with us, that's been really valuable. Yeah, thanks.
There's got to be some geological constraints on over consolidation ratio. I mean, if you're using an OCR of 3 or 7, how did it get that over consolidated? It's not like unless I'm wrong, these don't have a glacial overburden. There hasn't been a lot of erosion, of certain feet of soil at the site. So
yeah, I remember, I think it was maybe a year ago or something that Leon explained something, and you thought it makes sense, and I think it probably makes sense. Maybe it's a fluctuation of water in Columbia River or the drainage canal that changes the water table. Maybe that contributes to OCR, but I don't know.
At our site, I think potentially like water table fluctuations and just desiccation from like floodplain deposits, desiccate by crust, more floodplain deposits, desiccated by crust. The other ones I think are also, well, the flood deposits are relatively recent, I would think, a couple 100 years old. The other ones, the OCR might get so high just because of time creep and it's about the yield stress versus a maximum cost for stress. The Missoula flood deposits are 10,000 years old.
Super interesting study, so we really need to see that, it's good stuff. Two-parter for you, well, for this sample number 3, what was the sample quality? I'm sure you assessed it for
We haven't, Dan, have you assessed? We haven't.
No,
Kayla,
it's,
have you assessed sample quality on this? Here?
I don't think I did for these ones, but it would be fairly easy to go and these methods.
Yeah, I think that would be super helpful and beneficial. So the follow-up is,